Okay, so this is the revision of the industrial electronics paper written August 2024. So I just want to us to quickly revise it. I will skip the instructions here for the sake of time in progress, but I do advise you when you are in the exam to go through the instructions. It's very important. So I'll go straight into questions. So there is question number 1.1 was saying, use the superposition theorem to calculate the current through the load resistor, which means this, right? So we want to use the superposition to calculate that current. Just out of interest, I might just want to state what the superposition theorem actually says. It says that in any linear multiple source network, the resultant current in any branch is the algebraic sum of all the currents that would be produced by each source acting separately. That's what it states, right? Again, I might just want to elaborate on that to saying what exactly is a linear circuit. We are saying any multiple linear source network. What exactly is a linear circuit? It's a circuit where resistance, capacitance, and inductance do not change with the change in voltage or current in the circuit. Right, so it's good to know that. Okay, so how do we apply? How do we do it? How do we calculate the current using the superposition theorem? Okay, so here's what we do. First things first, we will short circuit one of our voltage sources then. Right, so I will start by short circuiting V2, this source here. So short circuit V2, right? Okay, so the 10 volt source is the one that we want to short. Okay, that's the one we want to short circuit. Okay, so it means our circuit will now look like this. It's very important now to know that this is now how our circuit looks like, having short circuited. Right, so here we are. Okay, this is our new circuit now after the short circuiting. Right, there we are. There we are with our resistor. This side, the 23 ohm resistor is now here. Then the 24 volts is here, right? And of course, the 9 ohm resistor, the 20 ohm resistor, the 23 ohm resistor, right? And then the 14 volt source is the one that is still remaining. So we have short circuited the 10 volt source is no longer there, right? So what do we do now? We can now calculate considering that only, right? So let's perform the calculation then. So we are saying, right, let's calculate RT, having done that. So RT is going to be given by, this is what happens. Of course, I just want to emphasize on that to say, we follow the conventional flow of current. We know that when current reaches this point here, it will obviously subdivide such that some current will go towards this direction, some current will go towards this direction, which means this resistor, the 9 ohm, is in series with these two resistors, which means we call their total resistance, we call it their equivalent resistance. So we are saying the 9 ohm resistor is in series with the equivalent resistance of these two. But what are these two? They are in parallel. How do we see that? By the division of current. That is, okay, they know very well that resistors that are in parallel are current divider, or a parallel combination is a current divider combination actually. Right, so having said that, it means we can just go straight and say 9 plus, right, for the parallel combination, we are just saying product over sum, since there are only two of them. So 24 multiplied by 23 over 24 plus 23. It makes us to go quicker to the answer directly. So we end up having 9 plus 11.745. 11.745 becoming the equivalent resistance of those two that are in 20.7468085. So let's round that to 3 decimal places. Of course, we can get 20.745 ohms. Right, so that marks our total resistance. Then from there, what else do? We now calculate the total current using that total resistance that we now have. So it means IT is here, right? So it's going to be 14, our voltage that we have there, divided by the 20.745 that we have, and that is giving us 0.675 amperes, right? That marks our current. Right, from there, we now calculate I1, the current that is now flowing through the load resistor RL. Apparently, our load resistor, as we can see from that, is the one that we have there, right? The 24 ohm resistor, it is our load resistor. Forget that, okay? So it means we now want, let's call it I1, the current through that resistor RL. Right, so how do we calculate it? Right, the quicker way of doing it is we can use the current divider rule. We can just use the current divider rule. What does the current divider rule says? It says I1, meaning if this is our I1, I use the second diagram that I've drawn here, calling this my I1 and this marking my I2. So of course, there is the I total current coming from the supply. It is the same I total that will go back again to the what? To the supply. So I1 is equal to R2. So my R2 becomes the other resistor in the other branch. So R2 over R1 plus R2 multiplied by I total, the total current. That's what basically the current divider rule state or says. So it is apparently the one that we need, or we can just use. So we are saying R divided by I total. So what is important is to know what is it that we refer to as that. So that's 23. That's our R2 as a matter of fact multiplied by 0.675. So the current divider rule, just in simplicity, it's nothing other than just a ratio that is being brought out to try and bring out the division of current that will take place, whereby we are saying current indeed will be divided, but it will be divided proportional to the sizes of the resistors. That's basically what is happening there. Okay, so we have 23 over that, which is giving us multiplied by 0.6, so it's going to give us 0.33 amperes. That marks our current through the resistor RL having short-circuited V1. What is the next? So this time around, we are not short-circuiting V1, we are not short-circuiting V2. Okay, so let's V1, the short-circuit V1, it is short-circuit V2 on the other time. Now we are is the one we are now short-circuiting. So I'm going to demonstrate here the diagram, how it's going to look like. There is our diagram here having short-circuited V1. So there we are. There we are. Okay. 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 So there's our resistor there. Part of my diagram is a little bit poor, but nonetheless, now what I'm trying to demonstrate is very much clear. So there's the 9 ohm. It's remaining on its own now with the 14 volt source having been short-circuited. Right. So we have the 10 volts now as our source. We again start RT is going to be equal to, so now we are calculating the total resistance considering this 10 volt source. So our current is now going in this direction, the conventional flow. When it reaches this node or this junction, current will divide. Some current going towards this direction, some current going towards this direction. Automatically, that's basically what is going to happen. Okay, so it means that the 23 ohm resistor is in series with the equivalent resistance of these two, which means the 24 and the 9 ohm are the ones that are now in what? That are now in parallel. So we can just go straight and say RT is going to be 23 plus, right, these two, they are in parallel, so product over sum, that's 24 plus what? Plus 9, product over sum. So basically that is giving us 23 plus 6.545. That is the resistance of this that are what? That are in parallel, the equivalent resistance, right? So that is giving us then 29.545 ohms. There we go. Right. So it means now we can therefore calculate IE1 again. I'm calling it IE1 being the current through the 24 ohm resistance. So we can actually call it IE1, we can call it whatever that we can remember. But of course, IE1 or IE2 can be a better choice because indeed it is the load resistance that we have there. All right. So I1 is equal to, from using again the voltage divider rule, we can still use the voltage divider rule to say R2 over R1 plus R2. Okay, I needed first to calculate the total current. I have to calculate the total current. Let me just calculate the total current first in order for me to calculate I1. Okay, so IT, the total current over RT, because as I will use the current divider, I will still have to use the total current as well. Okay, so that's VT over RT, that's 10, divided by the total resistance, 29.545, and that will give me 0.338 amperes. That marks my total current using the 10 volts source, okay, amperes. There we are. Right, so we have our total, Okay, just like that, amperes. Okay, we have our total current. Now that we have it, it means it's possible now to calculate the current through the 24 ohm resistor. Apparently, that's our load resistor. So I can now safely use now the current divider rule again. So I'm gonna say, so that's I1 is equal to R2 over, which in this regards, what are we doing? What's happening? We are saying the current, calling this my I1, current that will flow through the 24 ohm resistor, and calling this one my I2. Remember, we are considering the 10 volt source. So it means then that I1 is my current. It's going to be equal to R2, marking this one as my R2, over R1 plus R2, the sum of the two, multiplied by the total current, which means in this case, my IT is the current being supplied by the 20 volts source. Okay, so it means I can then substitute that knowledge or that into the formula. That will give me then R2, which is in 9 over 24 plus 9 multiplied by 0.092 amperes. Then what do? We then now superimpose the two. So it means now we can therefore say total current through the 24 ohm resistor, IL, is going to be equal to the sum of the two currents that we calculated separately, the 0.33 we calculated initially, plus the 0.092 we now calculate upon short-circuiting V1. So the two short-circuited currents will now mark our current through the IL, through the load resistor, having been being supplied by the two sources separate. That marks our current. Right. Let's quickly go to the second, Norton's theorem. That's our second question there. State Norton's theorem. Okay. So Norton's theorem simply says that any linear circuit can be simplified to an equivalent circuit consisting of a single current source and parallel resistance that is connected to a load. That's what Norton's theorem says. I might just want to in much time. I just wanted us to know that actually we are simplifying our circuit to represent this, what we see here, whenever we are applying Norton's theorem. So we are saying, considering or assuming this is our load resistance here, we call Norton's equivalent circuit. So that Norton's equivalent circuit, we have to include what we call I Norton, the Norton's current, and it will also have to consist of what we call R Norton, that's Norton's resistance. That's what we'll be having. So this is now serving as our R Norton. This is now serving as our I Norton. So I will not go into much detail as the question is not asking much about that. So let's quickly go on to the next question. Question number 2. Use Thevenin's theorem to calculate the current through the fifth. To use Thevenin's theorem. So we would want to do that. Okay. So number 1. So the things first. We would want to calculate, I would want to calculate Thev, we call it Thevenin's resistance, right? Thevenin's resistance is calculated by open circuiting, removing the source and replacing it, okay, with an open circuit. So we're just removing it, actually, the load resistor. So we end up having this. So that's the first step that we are taking there. Right, and then we have the resistor here, and we have another resistor here. Okay, and we have another resistor here. So what have we done? We've removed now the source, the load resistor is removed. Right, so we have the 25 ohm resistor here. We have the 20 ohm resistor here. We have the 40 ohm resistor V1 there. That's the 10 volts. Right, so here we are. This is the circuit that we have. Okay, so having done that, it means looking in, which means from where we have removed our source, we now our load resistor, we now look in and then calculate. That's actually what we have to do in order to calculate RThev. So we are saying looking in, RThev therefore shall be right. From that position, we can see that the 25 ohm resistor, if we are now going in this direction, assuming that the conventional flowing is now from this direction, it means the 25 ohm resistor is actually in series with these two, whereby these two are now in parallel. So, wanting to calculate RTF, it means this source will not be of much in use at that particular time. We are just replacing all voltage sources with a short circuit and, of course, current sources with an open circuit. So we have this as our circuit. We have them looked in. So what do we get? RTF, therefore, is going to be equal to 25 plus 20 times 40 over 20 plus 40. Why are we doing so? Because of that, we can therefore safely calculate RTF, and that will give us, definitely it's going to give us 1325 plus 13.333, right? The equivalent resistance of these two, which therefore is going to give us 38.333 ohms, right? That's what we have now is our RTF. That's marking our RTF, okay? So we now want to calculate ITF. We now want to calculate, right? So in calculating ITF, right, we will have a circuit of this nature. This is the circuit we are now having, right? We have brought back our source, but when current flows now, since we have removed the load resistor here, it means that there is no current that will go through this route or this path. All the current, we have to take this route. So because of that, when we are calculating I total, the total current of the equivalent circuit of our Thevenin, of Thevenin, so Thevenin's equivalent circuit, which means this is the path that the current will only take. So we are saying 10, the total the total voltage divided by what now is our total current, our total resistance, because remember it's V over what? It's V over R over R, right? So we know that current is always equal to V over R. So which specifically are we considering as the total voltage of the source? We're saying two, the 40 and the 20. They are now in series because as the current is flowing, remember that resistors can only be in parallel when current has been divided between them. But from the look of things, if we have open resistor here, it means the current that 40 ohm resistor will experience will exactly be the same current that will pass through the 20 ohm resistor. So it means the two are now in what? In series. So we add them, 20 plus 40, that marks 60. So we can now divide that, and it's going to guess, right? It's just my choice. We could have just divided that. Fine. Then we now calculate V third. Now say 1 over 6, the current that we call system voltage is our voltage that we want to calculate. So we are now saying resistor. So 1 over 6 multiplied by 20 and 333 volts. Right. Now that we have VTF, we now go to the formula that we use to calculate ITF. Right. So ITF, therefore, is calculated by is equal to VTF over RTF, right, plus RL. The loss is 3.333 divided by 15, and that will give us 0.062 amperes, right? So this is now 2, right? 2.2 is saying calculate the voltage drop if the value of the load resistor changes from 15 ohm to 35 ohm in question 2.1. If the value of the load resistor changes from 15 ohms to 35 volts. So basically, everything will remain the same, because remember we had removed it when we calculated RTF, we had removed it again when we calculated VTEV and ITEV. So it means now when you calculate the new current now, we can just say it's going to be equal to 3.333 VTEV is still the same, divided by RTEV still has not been affected, it's still the same, 38.333 plus, now we use the load resistor, that the new load resistor now of 35 ohms, 0.045 amperes. Then when we now have the current is equals to I times R, of course, which is 5, multiply it by, that becomes the voltage drop across the 35 ohm resistor, the new 35 ohm resistor. That's 2.2 for us. So let's quickly go to the next question. Question number 3. Question number 3 is saying choose the correct 3.1, choose the correct term for those in brackets and write it next to the question number. The maximum, so it is the maximum current flow in a series resonance circuit is called an acceptor circuit. So it's called an acceptor circuit. That's what we have there. It might just interest us to know that when we are in a series resonance, it's actually the way we have the maximum response to current. And of course, we have the minimum impedance at that particular time, right? Then the 3.1.2, the impedance for a parallel circuit is purely resistive. That's current being at minimum. So that's now at parallel resonance. We are saying that's what actually is now called the rejector circuit. It might just good to note that. That's the rejector circuit. Actually, it means it's now the opposite. Current now is at its minimum, and of course, impedance now it is maximum. Let's go to 3.1.3. The quality of Z, the impedance of a part called dynamic impedance. Okay, so that's what is happening there. Let's go to 3.2. 3.2 is saying an adjustable frequency with a constant voltage of 300 millivolts is connected over an RLC serial circuit if the frequency is adjusted until there is a maximum current flow of 12 milliamperes at 4 kilohertz. Calculate the value of RLC if the Q factor. What can we calculate? Right, from the information that we've been given, it's possible to calculate ZT, the T over IT, which we have been given. So 3, we have been given the voltage there. I would advise often when you are answering question well, so it saves you time, the power of -3 divided by IT, the total current, which in our case again is 12 milliamperes. So 3, that's what we have there. So 5 ohms. Now, since we are at resonance is where we have the minimum. At series resonance is where we have the minimum impedance. Why? Because Z is now equal to R. So apparently R is also equal to 25 ohms. It's actually equal to 24. So we have determined R. We have just calculated R. Now, let's calculate L. Where can we get it? Right. Again, we ought to know quality factor we have been given. Q at series resonance is equal to XL over R. Hence, making XL the sub equal to R times Q. So we can now calculate it as 25 multiplied by 120, and that will give us 3,000. Then, how can we calculate inductance? Because the question is asking us that this is by the way, this is inductive reactance. This is XL inductive reactance. So we want to calculate L, the inductance. So where in the first place do we find how do we find XL in the first place? So it's equal to 2 pi FL. So making L the subject, it means we have XL over 2 pi F, 2 pi F then 3,000 divided by 2 pi multiplied by 4 times 10 to the power of, right? We have been told there that our frequency is 43, right? That's 10 to the power of 3 then. And simplifying that, it's going to give us 0.11936, right? Pressing the ENT button once, it's going to give us 119.63 times 10 to the power of -3, which is equivalent to 119.63 millihenries. It's just out of our own interest that we want to present our value in that regards, because no instruction was saying give your answer in millihenries. But it's, right, so that's our inductance apparently. Now the next question, okay, we want now capacitance. Capacitance, we shall find it from also inductance. We've just determined from our inductive reactance. We have just determined right now the XL. We have just determined it as 3,000 ohms. That's our XL, the inductive reactance. However, we have to remember we are at resonance, and at resonance, XL is equal to XC, because that's actually the one of the reasons that has caused Z to be equal to what? To R, because XL and XC are at par, they are equal now. That's what happens at resonance. Hence, because of that, because we are at resonance, it means that at series resonance, it means from the formula XC is equals to 1 over 2 pi F psi FC multiplied by 2 pi FC, right? It means 2 pi FC times XC is equals to 1, making C the sub pi FXC C, right? It means C is equal to 1 over 2 pi FXC. That's what we now have. XC we have made, means we can now substitute into the formula 1 over 2 pi. F, the frequency we have, it is 4,000. So that's 4 times 10, which is our capacitive reactance. Why? Because it is equal to the inductive what? Inductive reactance. And that is giving us 1,326 times 10 to the power of 1,326 times 10 to the power of -8, which is the same as 13,263 nanofarads. That's what has happened there. Remember, the unit measurement for capacitance is what? Farads, which means we have arrived. That marks our answer there, right? So basically, that's the next question. Right? The next question is now saying, explain how the Q factor affects bandwidth by means of a labeled characteristic curve. So we just want to draw and explain using that diagram. So it's just the drawing, because the instruction is said by means of a labeled characteristic curve, which means just wants us to draw the characteristic curve. Right, so I'll just quickly draw it here. There it goes. Okay. Okay. So amplitude, right? There we are. That's our amplitude, right? And then we have, okay, there it is. Slightly, a little bit, not that much used. Okay, there we are. There it goes. Then, right, there we are. There we are. Right. So that marks, we are saying this is our wide bandwidth. So this is where we have a low Q. This is where a low Q, and we have a wide bandwidth, right? Bandwidth, beta response. This is where we are, beta response, right? And then we also label here, right? We have a high Q. We have a high quality factor. So it means we have a narrow. That's why we have a narrow bandwidth. A narrow bandwidth, beta selectivity. Right, beta selectivity. Okay, then we can just illustrate. Right, my diagram here doesn't depict what exactly we want. Want something a little bit, okay, something like that. Okay, right. Just pardon my diagram a little bit. Just have to be showing a peak here. This is what we should have, something similar to this. Okay, so this part here, I just want to make it a little bit. Okay, so there we are. There we are. Okay, something like that. Like that. Okay, so that's our diagram there. That's our diagram we have. So just to know again that a low value of resistance can also produce a high quality factor and so low bandwidth and high selectivity. Just the diagram there. Okay, let's go to the next question. Right, 4. The question is saying, study the figure 3 above and answer the following. What does the above circuit represent? So that's a voltage regulator that is using a Zener diode that we've been given there. That's a voltage regulator with a Zener diode, right? calculate the values. The next question now is saying calculate the values of RS, RL, right? Before we calculate this, I just want to elaborate more on this diagram that we see. So we are saying this capacitor here is a simple filter capacitor circuit. So immediately after filtering, we then have a regulation where we want to have a voltage stabilized, our voltage stabilized. So we are saying the Zener can actually do that. So in order for it to perform the stabilization, it has to be connected in parallel with the load, like what has just been done here. That's why you see the Zener diode is connected in parallel with the load resistor. That's why you see what has happened there, right? So that this second diagram is what exactly is it? Okay. The next question there was saying 4.1.2, calculate the values of RS, RL, and the input voltage of 32 volts. If the input voltage is 32 volts and the output voltage is 16, the load current is 90 milliamperes and the capacity of the Zener diode is 8 watts. That's the information you've been given. The current of the load resistor we have been given, the load current there. So we can use that to calculate RL and the output voltage. Apparently, that's the voltage. And they easily say, then is asking is equal to V out over IL, the load current. So it's 10 to the power of -3, which is the 8 ohms. So we have the load resistance RL, right? Then we now want to calculate RS. Where can we start from? We can start from, I need us to, I'm not going to redraw. I want to use this diagram here to explain. Now look at the direction of the current. It's IS here. That's our current, which means our main current is IS coming from the supply. And then we have our two currents, IZ and IL. So IL that the question is asking is this, that the question had given us is this one. The one we were told is 90 milliamperes. It is the current going to the load, which is this one. So that's the 90 milliamperes. Right. So what is happening? What is happening is we have IS as the main current, which means according to Kirchhoff's first law, if we can use Kirchhoff's first law, it says that current entering a node or a junction is equal to the algebraic sum of course of currents that are leaving the node or the junctions, which means if IL and IZ are the two currents leaving the junction, it means IS is the current entering. So hence we can formulate an equation based on that, where we can say IS is equal to IZ plus what? Plus IL, right? So, and that will give us, of course, do we have IZ? We can how, right? Bear in mind that since the Zener, as I have explained, is in parallel with the load resistor, what else do they share in common? They share the same voltage. As a matter of fact, that's the reason why they have to be connected in parallel, because the Zener is capable of stabilizing the voltage, which means as it does so, it is doing it at the mercy of the load resistor. It's helping also the load resistor. So the load resistor will end up having the same voltage as that of the Zener. So it's good to note that that's the reason, basically the major reason why the Zener has to be connected in parallel the way it is. So we are saying in order to calculate IZ, why do we need IZ? Because we can use it to calculate IS. So IZ is equal to P over V. What is P? The power of the Zener, which is 8 divided by 16. That's VZ, that's V out as well, right? So we are saying VZ is equal to V out. It's important to note that. So we can therefore calculate it as what? 0.5 amperes, right? 8 divided by 16. How are we going to calculate IS? It's going to be equal to 0.5 plus IL. What is our IL? 90 times 10 to the power of -3, which is amperes, right? There we are, right? It means we can the current through the resistor RS. We want now to calculate VRS. We can call it VR, the limiting resistor, that resistor that we see there. Right? So that's VRS, the voltage across that current limiting resistor is equal to V in minus V out. Right? What is happening now? What is happening is, again, we are saying the EMF of a circuit in a closed loop is equal to the sum of the potential differences in that closed loop. Just loosely explained, that's what it is saying. So it means our EMF in this case, it's the V in the supply voltage, right? And our potential differences that we have are V out. Remember, V out and VZ are the same here, and we have also VRS. So these two, if we add them, they are supposed to give us V in. So hence, for that reason, it means VRS, by making it, of course, the subject. It means VRS is equal to V in. Remember, I said it's also equal to VZ, right? So it means it's 32 minus 16, which is giving us 16 what? 16 volts, right? There we are. And of course, having determined VRS, having calculated IS, it means therefore RS can be calculated. What is RS? RS is equivalent to VRS over, what does that give us? 16 divided by 0.5.119 ohms. That marks RS, the size of the resistor RS. That's basically what we could have done, right? Let's go to the next question. 4.2 is saying, list any 3 applications of the silicon-controlled rectifier. So the SCR has a widespread use, mostly in control circuits. So it is used for motor controls, relay control, heater controls, battery chargers. We can use it for power supplies, regulated power supplies, static switches, time delay circuits. Those are some of the applications of the silicon controlled rectifier. Okay, so let's go to 4.3. 4.3. 4.3, what does the circuit diagram in figure 4 below represents? Right, that circuit we see there is that of the SCR used to control the speed of a small motor. That's the circuit we see there. Okay, explain the operation of the circuit in question 4.3. So we want to explain its operation. So we say during the positive half cycle of the input signal, the SCR will turn on and the anode to cathode will drop to the conduction value, resulting in reduced gate current, right? Then we say during the negative half cycle of the input signal, that's the negative, right? The SCR will be off. This will result in the diode is included to allow only positive pulses to the gate of the SCR and prevent negative pulses from going to the gate of the SCR, right? RV is used to adjust the conduction angle, thereby adjusting the speed of the motor. That's the explanation, which was expected, right? Let's quickly go to question number 5. Indicate when true or false next to the question number 5.1.1, 5.1.3 in the answer book. Give a reason for the answer. In isolation, transformer transfers power from primary to secondary through both conduction and induction, right? Apparently that's false. That's not correct there, because an isolation transformer doesn't actually do that. Rather, what it simply does is it actually has a separation. It can't do that. So that's what actually an auto transformer that can do that as a bit of effect, right? Just out of interest. An auto transformer prevents harmonics from transferring from one to the other side. That's also not true. That's false there. Apparently, that's also what an isolation transformer can also actually do. So it's not correct. Right, let's go to the next question. The next question is saying, study figure 5 below and answer the questions that follow. What type of a rectifier does the above waveform represents? It represents actually the half-wave rectifier. That's a half-wave rectifier there. Okay, half-wave rectifier circuit. Right. It's the half-wave rectifier circuit with a capacitor filter. That's a half-wave rectifier which has a capacitor filter. right? Choose the correct term for those in the brackets. The above graph is actually an output waveform. It's always having a sine wave. That's an input signal before rectification has been done, right? So just mention that out of interest, right? Calculate the ripple voltage, the output DC voltage, and the percentage ripple voltage. So we'll start with the ripple voltage. All right, with the ripple voltage, VR RMS, right? VR RMS is equal to, it's equal to VR peak to peak over 2 root of 3, right? So we need the VR this one actually, right? And it's 11, and here we have 9, right? So that's the VR peak to peak given by 11. So VR peak to peak is equal to 11, right, minus 9. So 11 minus 9, that gives us 2 volts. So it means, therefore, we now calculate VR RMS as 2 divided by 2 root of 3, and that will give us 0.577 volts. That's VR RMS then, right? And then that can lead us now to VDC. We now calculate VDC. VDC is the equivalent to VM minus VR peak to peak over 2, right? So with that, it means we can now say VM being 11 minus VR peak to peak that we have calculated, which is apparently 2 divided by 2, and that will give us 10 volts. Okay, let's go to the percentage ripple voltage. Right, percentage ripple, that's the ripple factor there, right? The ripple is equal to, right, so the percentage ripple is equal to VR RMS. It's actually ratio of the RMS and the VDC, right? 77 divided by 10, and that gives us 0.577 times 0.577 multiplied by 100, and that will be 0.0. That's 0.0 there. Sorry about that. That's a 0.0, right? That's 0.0577. Okay, so that's 5. Okay, right. Let's go to question number 6. It's saying differentiate the basic operation between a principle for DC and AC analysis of a BJT amplifier circuit. Right. DC operation first. The operation of the DC. So first, we want to explain the DC operation. When the transistor voltages and currents are constant, which means when they are not varying, the transistor is said to be operating in its state condition. We call that a state condition, right? So it's operating in state. That's DC. The operation, DC operation. Now, AC operation. We are not explaining AC operation. When transistor voltages and currents are varying, which means are not constant, the transistor is said to be operating in its unsteady state condition, in unsteady state or dynamic condition. That's the explanation that was expected of us. Right, let's go to 6.2. 6.2, the voltage A amplifier is input voltages of 3 volts minus 7 volts. Assume that the input resistance are all equal to 5 kilo ohm and the feedback resistance 25 kilo ohm. Calculate the output voltage, right? For the head, which is one of our amplifiers, V out is given by the formula negative RF plus V2 over R2 plus V3 over R3, right? So we can then calculate it as, right, we've been given RF, that the feedback resistance is 25. So we shall say negative 25 times 10 to the power of 3 divided by, that's V1, that's 3, over 5 times 10 to the power of 3, that's our R1, right, plus negative 5, right, over 5 times 10 to the power of what? Of 3, right, plus 7 over 5 times 10 to the power of what? Of 25, 5 times 10 to the power of 5 plus 7, right? And 25 volts. So we can end up having that. Right, let's go to the next question. Start the figure 6 below. Answer the questions that follow. Identify the operational amplifier. Right, that's a comparator. It is a comparator actually. So that's a comparator, and choose the correct term for those in bracket. The above operational amplifier is used with or without. Apparently, for even from as you can see, it's without feedback. It doesn't have a feedback, so it is used without feedback. The next question is saying draw a neat label file, a labeled diagram of that operational amplifier. All right. So with 6.63, which was asking the input and the output waveform of the comparator, which is our above op-amp, this is the input and this is the output waveform. Right. So basically, what we should also have to know is that this is quite an interesting op-amp, that it doesn't have a feedback. So it has an open loop arrangement. However, the open loop gain is so high that if V2 minus V1 exceeds approximately 100 microvolts, the op-amp saturates, right? And if V2 is such that it is greater than V1, the V out, the output voltage, will then rise to VCC, which is this positive VCC. And if V2 now is such that it is smaller than V1, then V out falls to negative VCC. And this reaction is the one that is clearly being shown here on the output waveform. Right? So the op-amp is then behaving as a two-state digital device when it's like that. So with the VO, the output voltage switching from high to low in this form. So that's why you see the output waveform is now like this. And it is used as a comparator often to compare voltages. That's the purpose it is normally used for. I just mentioned that out of interest, but the question just wanted only the input and the output waveform as we have indicated them there. So question number 7 is of a neat labeled sketch of a simple transducer, how you would measure the displacement with the potentiometer. So it's just the data come out. So with our diagram in that nature, we are saying we have our R1, we have our R2 together with our galvanometer there. They are now forming a Wheatston's bridge. That's the bridge which has been formed there. So basically, this was our diagram, how it was supposed to come out with the shaft to the potentiometer as indicated. Time 7.2. Name 3 factors that would influence the capacitance of the capacitive transducer. Number 1, the area of the plate. Secondly, the distance between the plate and also the dielectric constant. So it's not in order. There is no order of arrangement. I'm just mentioning them. So those are the factors that can influence the capacitance of the transducer: area of the plate, distance between the plates, and the diameter. 7.4. What does LCD stand for? Liquid crystal display. 7.5. Name 4 types of LCDs. So we have twisted pneumatic. We have in-plane switching, we have the advanced fringe field switching, we have the vertical alignment. So that marks the end of our revision of the paper, right?